All right. So, Professor Carafit here, coming to you from the Bio Bunker, and we're continuing our discussion of energy. Um, we know energy can be transferred, some will be lost. Now, some of it's not lost, right? Some of it is used by the bear to stay alive. And that's what we're going to talk about in the next few slides, that energy that is actually used to do work. And that's known as free energy. The amount of energy that's free to do work, the energy that won't be lost is heat. And the fancy way to say it is Gibbs free energy, which is often symbolized by a G, kind of a G that's italicized. That's the energy available to do work. And what do we mean by work? Well, let's think about chemistry. We're talking about the work of making and breaking chemical bonds. And the way we calculate this is change in free energy. Change in free energy. Delta, that triangular symbol is delta. That means change. Change in free energy is the amount of energy in the final state of the molecule minus the initial state. So how much energy do you have at the end compared to how much you started with? Okay? And we've talked about entropy before, and I just wanted to restate it again. Every time energy changes or is transferred, some is lost as heat. Heat is the random motion of particles. Entropy is a measure of that disorder. I just want to point that out again because it comes up. You'll learn a lot more about that in physics, I'm sure. All right, so chemical reactions produce changes in free energy. And so if we have a reaction with a positive change in free energy, that means we've had an increase in free energy. Okay, it's gone up. Products of a reaction have more free energy than reactants. You can see that in this graph down here. It's kind of hard to see, I'm sure, but free energy is on the x-axis and time basically is on the y-axis. And we start off with chemicals with very little energy and we end up with chemicals with a lot of energy, right? That's positive delta G. That's an endergonic or anabolic process. Endergonic meaning energy came in. Anabolic means we've built something big. We built something bigger. That doesn't just happen by magic. It takes an input of energy to make that happen. And endergonic reactions, an example would be, or once again, endergonic reactions, an example would be like taking carbon dioxide, CO2, and gluing it together. You take six CO2s, and you can glue them together with a few other things to make C6H12O6, which is glucose. So that would be an endergonic reaction. You've built something big, and you've had to put in energy to make that happen. Negative delta G reactions are like the one down here where you had a lot of energy in the molecules you started with, and the molecules at the end have very little energy in them. That's like this reaction here backwards. Taking sugar and digesting it and using it to run your body, you release CO2 in the process. So products have less energy than the reactants, less free energy. This is an exergonic reaction or catabolic process. So we break things down. That's why it's catabolic and it released energy, which is why it's exergonic. An example, once again, breaking down carbohydrates such as glucose to extract energy. All right, so once again, when we calculate all this, it's the amount of energy in the end of the reaction minus the amount in the beginning. And if you get a positive number, then it's an endergonic reaction. If you get a negative number, then it's an exergonic reaction. Okay. Here's an example. Here is C6H12O6. This is glucose. If you don't know, you should memorize that formula. That's an important one in biology. Plus oxygen gas, 6 oxygen gas molecules, O2, that's molecular oxygen. That's what you breathe. When those two react, you get 6 carbon dioxides and 6 water molecules. Okay? And when that happens, you've lost 686 kilocalories. You know what kilocalories are. A kilocalorie is the same thing they call a calorie in like a can of Coca-Cola, right? It's a unit of energy, okay? So you lose 686 kilocalories per mole of molecule. If you don't know what a mole is, look it up. It's a unit in chemistry. Oops, sorry about that. I hit a button. It's a unit in chemistry talking about how many molecules there are in a solution, okay? 6.22 times 10 to the 23rd, or that kind of a thing. I'm sure you've heard of it. But per mole of glucose, When you convert it to CO2, you'll lose 686 kilocalories per mole of glucose. Likewise, if you make a mole of glucose and you glue a bunch of carbon dioxides and waters together, that's going to be a positive delta G, a positive increase in energy of 686 kilocalories per mole. Okay, so when you break sugar down, like going in this direction, you started off with a lot of energy, and then CO2 down here has very little energy in it. If you go the other way and you take CO2, and you could say and water, I didn't add the water, but CO2 has very little energy in it. You add energy in, and you end up with glucose up here. That would be an endergonic reaction. Okay. Now that, and we know that in this case we will have lost 686 kilocalories per mole, and here we will have gained 686 kilocalories per mole. So bear in mind that when you have a lot of free energy, like here are 3 examples: gravitational motion or falling, diffusion, or a molecule, a chemical reaction. So this is glucose here. And there's a person on a diving board, and this is a high concentration of something. Okay, they're not stable. These molecules won't stay that tightly compacted. This molecule will not stay together forever. This person will not stay on the diving board forever. But then a spontaneous change will occur. Once again, spontaneous does not mean instantaneous. It just means it will happen. This person will fall. This stuff will spread out. This molecule will fall apart. And at the end, we have less free energy at the end of the reaction. This is more stable, meaning the person will stay in the water forever if they don't crawl back out. These molecules will stay spread out. These molecules will stay broken apart. It's more stable, but there's less capacity to do work. So in each one of these cases, we're going from high energy to lower energy, and that is spontaneous. Now, when you go the other way, from these conditions to the conditions at the top, that is not spontaneous, meaning it will never happen on its own without an input of energy. So we can see this once again on a column graph. Oops, sorry about that. Here's a column graph. We have reactants and products, and this is a figure from your textbook here. If the reactants lose energy, energy is lost into space, and the products have less energy than we started with, so our change in delta G is less than 0, so like it's -10 or something. That means we've lost energy. That's an exergonic reaction. Energy is released. That kind of reaction is spontaneous. It'll happen all by itself. Just like a car sitting on top of a hill will roll down that hill all by itself, even without the engine on. But a car will not drive up a hill without an engine on. A car going up the hill would be like this example here, an endergonic reaction. So that's when you have low energy to start with, and you end up in the product with more energy. To do that, you have to have an input of energy. So a car can drive up a hill, right? It can do that, but it has to burn gasoline to do that. There's an input of energy required to make that happen. So that's an endergonic versus an exergonic reaction. And your body is doing both of these kind of reactions all the time. And we'll talk a bit about those kinds of things here in the next lecture video.